Okay, good morning. I wanted to take a moment to walk through this simulation, make sure that you can understand what to do at each part. Most classes, I will walk you through this myself, but first hour I will have a sub, so I want to make sure I had a clear-cut key of how to go through this. So first things first, first name, last name. I apologize, this is Mr. Yankee form, so sometimes he separates these two, but please do. And so we're talking about light refraction. Remember, light refracts whenever it travels at an angle into a substance with a different refractive index. Refractive index is also called optical density. Different substances have different densities, which affect how fast light travels through them. The change of direction of light is caused by a change in speed. So, for example, when light travels from air into water, it slows down. It causes it to continue to travel at a different angle or direction. So it's going to turn as it hits a different density of medium. So when light travels from air into water, it slows down, causing it to change direction slightly. That change of direction is called refraction. When light enters a more dense substance, which has a higher refractive index, it bends or changes directions more towards the normal line, that imaginary perpendicular line to the surface. The amount of refraction depends on two things. It's the change in speed. If the substances cause the light to speed up or slow down, it will refract more. And then the angle of incidence rays. So it depends on the angle that it's coming in. If the light is entering the substance at a greater angle, the amount of refraction will also be. So kind of like if it's coming in at a steeper angle, it's going to bounce off at a different angle. Whereas if it's 90 degrees, it'll slow down, but it won't change direction. All angles are measured from an imaginary line. We call that the normal. If light enters any substance with a higher refractive index, such as air to glass, it's going to slow down. The light is going to bend more towards that normal line. If light travels into a substance with a lower refractive index, such as water, it's going to speed up. It's going to bend away from the line. So I'm not going to watch this video, but I would expect that you will. So which statement best describes what you are seeing? Is what you see is light is light waves are light is traveling in curved paths, because it's going to bend differently in the water than it will in the air, than it even will through the glass and through just through the air. So light's going to bend differently through all these substances. So that's going to travel in curved, light waves are changing direction. I'm sorry. Again, this is not mine, so I have to sometimes try and put my head in the understanding of the teacher who writes this. So yeah, light waves are changing direction because that's why they're bending. That is that refraction. What is causing light to bend that way? Our waves are slowing down in the denser medium. So remember, as the medium is more dense, it's kind of like I always use the examples. If I'm running on the beach, I'm fine, but once I hit the water and start running through the water, because the water is more dense, I slow down in my running. I'm not a light wave, but light waves do the same thing. The denser the material, the more it's going to slow down. Okay, and as he says, look carefully. How many different cases of refraction can you observe? Well, I see the water in glass, the air in glass, and just the air. So I actually see three levels of refraction, because it is going to bend a little bit and change, not as much in the glass, but it does change. But you can see definitely here that there's a broken section, and not so much here, but they are three different mediums I'm looking through, so there are three different cases of refraction. We talked about prisms. When white light shines through a prism, we kind of bend that light into its component colors. Violet light refracts more than red light. So we can use a prism to show the 7 colors of the spectrum that make up white light. The explanation for the colors separating out the light is the waves. Each wavelength has a different frequency. So red light has a longer wavelength than violet light. The refractive index for red light and glass is slightly different than for violet light. Violet light slows down even more than red light, so it's refracted at an greater angle. So for glass, for red light, it's 1.53. For violet, it's 1.53. That slight difference is enough to cause those wavelengths to be refracted differently, and it's going to cause those colors to separate out. So what's happening in this image? We see that as it's going through a prism, white light is being separated split into different wavelengths of light based on the amount of refraction each wavelength goes through, which is our next question. What is happening to cause the results you observe? White light is made of different wavelengths of light that refract differently from the other, and that is the actual answer. Okay, the flashlight color bleeds. That can happen in some materials, but that's not what's happening in a prism. Light is not traveling in a curved path, and it's not colored glass, it's clear glass. So what we're seeing is white light being broken up into its component colors. And this is exactly what this shows. So as white light comes in, it gets broken up into different colors because it's different frequencies and it's different wavelengths, and they refract at different amounts. Okay, for the next one, you're going to go ahead and open this simulation. Give it a second to load. Okay, we're going to start with the intro. Okay, it says press the red button to turn the laser on. We're going to see what happens when the laser goes on. So let's go ahead and turn the laser on. And we see two things occur. We see the one that as the light goes from the air to the water, it's going to bend or refract. We also see there's a light wave reflection. Okay, so we're going through air and water. Those we don't worry about the index as a reflection so much, but we see that light is refract. So two things: light is refracted and light is reflected. Well, that's a bad question. Sorry. What happens to the light when it enters the water? Okay, so the change color, light changes direction, light changes color, light speeds up, light slows down. There are more than things happen. So what's happening is if light is going through from air to water and the index of refraction is different for water, it's denser, it's going to slow down. And that's going to cause that light to bend. So the light is going to change direction and the light is going to slow down because it's a denser medium. Okay, now we can use this intensity meter and measure how the light intensity is. And when we're up here, we have 100% of our intensity from the laser beam. When we leave and go into the water, we see it goes down to 94.71. So the fact that this is being reflected, this is not that different amount. Well, I guess it is. So what is happening is all of the light is being absorbed by the water. None of the light is being absorbed by the water. 94.71% of the light is being absorbed by water, or 5.29% of the light is being absorbed by water. And what we're missing is at 5.29%. That's what that difference is between 100% and 94. So what's happening is as it ends the water, because it's slowing down, some of that is being absorbed. I don't disagree with that, actually. And how can you be sure your answer to the last question was correct? The reflected and refracted intensities add up to the original intensity. The intensity level is 0 by the time it reaches the bottom of the water, which it does not. The intensity in the water is the same as it was before the light entered the water. That's not the case. So it's the reflected and the refracted intensities add up to the original. So if I take that 94.71 of the refracted, I add it to the 5.29 of the reflected, and what I get is the total of 100%. Okay, it says drag the protractor from the bottom line and line up the vertical center down to the normal. Okay, so we can go ahead and do this. So we're going to move our protractor. We want that notch right at that normal. We want the water line right at the set. Okay, so as we look at that, what is the angle of the incidence? Angle of from as measured from the normal. So if we're measuring from 0 to here, we're about 30, 40. That would be 50, so about 45 degrees is our angle. If I measure the reflection, I should get the exact same. Remember, the law of reflection says that the angle of incidence is equal to the angle of reflection. So if I look at this coming off, I also get 45 degrees. So whatever comes in, it comes out. All right. Now, as we go to this section, it is on prisms. So we're going to change to prisms. Turn the laser light on, clicking the red button, drag the triangular prism in the lightened path. You can use the round rotation handle to rotate the prism as it handles. So we're going to use the triangular prism, move it up here, use the laser, and we can rotate the prism. So how many times is the light refracted when the triangular prism is in the laser? It's not. It's not. Okay. How many times is the light refracted when the triangular prism is in the laser? I'm going to say he meant the laser is in the triangular prism. So if we look at this, it refracts once, and then it refracts twice. Once when it comes in, once when it comes out. I think that's the right answer. Okay, we're going to move the square prism in the way. So we're going to get rid of this, move up the square. Now, how many times is the light reflected by the triangular prism? I didn't mean to open that tab. I apologize. So as I rotate this, I really only have that one. It refracts only twice as it goes in and as it comes out. So how many times it comes? One goes in and goes out twice. If these are not the right on the application on your grade, I will double adjust these because these are the way that I'm reading these. Again, this is not my simulation, so sometimes I have to make accountability for what another teacher might be thinking. So I will do my best to adjust this application grade. At the bottom of the simulation, click on the More Tools, turn on the laser light by clicking the red button, drag the speed meter so it touches the point screen. So we're going to go to the More Tools option, which is behind me. No, it's not. Where's my More Tools? Oh, More Tools is right here. I apologize. All right, so we're going to go ahead and turn the laser light on, clicking the red button, and we're going to use the speed meter, which is this. So we're going to click on this, use our speed. We see it's moving at the speed of light as it's going through the air. Now, what we notice is as it hits the water, it's going to slow down as we would expect because the water is more dense. What we see is that this new speed is about 0.67 C. That's 0.67 C. Oh, I'm sorry. As it leaves the laser, it's the speed of light, which is 1 C. C is actually a representative value for the speed of light, as in Einstein's E equals mc squared. The C stands for the speed of light, which you learned today. What is the speed of the beam as it bounces off the glass? I don't have glass. Oh, it is glass. Okay, so as it bounces off, the speed changes to, it does not change. It comes in and comes out at the exact same speed as it reflects. So as it bounces off the glass, it is still going the speed of light. It's reflecting the speed of light. And why would that be? Well, because it's still going through air. It's not going to change the density of the material, so it's still going to travel the same speed. However, when I look at the speed of the glass beam in the glass, that's when I notice that the speed has dropped down to 0.67, or basically 2/3 of the speed of light. And why is it slowing down? Because it's more dense. And it's harder to get through. Okay, so we drag the protractor from the bottom left to the center line vertical. So we go ahead and do that. Move our protractor, and again, we put that that dotted line right on the normal there. And once again, we see it's coming in at 45 degrees. Can I not move this? Okay, so 45 degrees. So what it's coming in at. What is the angle of refraction of the light inside of the glass as measured from the normal? So if I'm measuring from the normal, I'm going to move my speed marker here. So this is the angle of refraction. Here's my normal. So it's roughly around 5, 10, 15, 20, 25, about 27 degrees. 27.5 degrees is my refraction angle. So why is it different than we always said the angle of reflection is equal to this is the angle of incidence. This is not reflection. This is refraction. This is it bending because it's changing its speed as it travels through the different mediums. Okay, so we're going to change the bottom half of the material from glass into water. We see that the line changed a little bit because the index of refraction has changed a little bit because it's not as dense. The water is not as dense as glass. I've run into water and been okay, run into glass and not been okay. So what is the speed of light as it leaves the laser? I'm going to give you a second to guess on this because you should know. As it leaves the laser, I would expect that speed is the speed of light, which it is, 1 C. Now, as it bounces off the water, as I said before, if it's still going through the air, the speed shouldn't change. And it's still going 1 C. So when it reflects off the glass or off the water, it's still going the speed of light. Now, what we should expect when it goes into the water, it should be going faster or slower. Well, because the water is more dense, it should be going a little bit slower. And we see that it's actually going 3/4 or 0.75 the speed of light. So we see that, in fact, it did slow down. Okay, so we drag the protractor. The protractor is already there. What is the angle of refraction now? And now we're right about 31 degrees. Let's see what he marked this. Well, he's about 32.5 degrees is what he marked it as. And I'll make sure these are the right answers on my class. These are going to be the right answers as I see it, so I will change my key to fit this. Which material, glass or water, caused the biggest change in the speed of light? What we saw was that the bigger difference was between the air and the glass, because it was 45 and it went down to 27.5, whereas it was 45 and it went down to 32.5. The bigger difference was between the glass, which makes sense because the glass is more dense. It's going to be harder for that material or that light to go through the glass. I can speak. So which one caused the biggest change in direction of light ray? It was the glass. That refracted it a little bit more. Based on what you know about electromagnetic waves and density, how does density affect the amount of refraction of electromagnetic waves? And what I would expect is that the more dense a medium, the more it's going to be refracted. The more the wave has to go through, it's going to bend a bit more. It's going to slow down more. As we saw, for water, which was not very dense, it was 0.75. But for glass, which was very dense, it was 0.67. So it was a much difference. All right, moving on to the next page. Okay, I have shown this in class, but if you ever wanted to see it, these are just videos you can watch that kind of shows the flipping arrows, something kind of cool you can do at home. Some different laser experiments, how a laser works. You are welcome to watch these at your leisure for additional information, but what I'm looking for is the application grade. If you have any questions about that, you can see me doing study hall today. For most of my class, I will walk you through this myself. But for my first hour class, I do apologize. I'll have a sub. So I wanted to make sure I created this video for your use. When you are done, submit. I'm not going to submit. Well, I guess I will submit because I want to see what the score would be for my answers here. So I'm going to view my accuracy. And as I said, this is going to be my key. So I'm going to go right now. And if this aren't the answers Mr. Yankee had chosen, these are the answers that I will make sure that I've checked. And why was that giving me a grade? Come on. So in a day and a half when this loads, hey, you got my name right. Come on. Did I miss anything? Come on. Nope. So what is his response? So this one, I'm going to keep this. And I'm not a big fan of this question in the first place, but I'll adjust this. I will not mark that wrong on yours. Really doesn't make a lot of sense, because none of the light's being absorbed. So maybe none of the light is being absorbed. He's talking about the refraction index. Maybe that's what he's talking about. So I'm going to go ahead and change that to none. But for my class, I'll keep it that way. Again, I'm allowed to disagree. These are okay. These are okay. These are okay. It looks like I sort of understand Mr. Yankee's thinking on most of this stuff. What is his key? So I will double check this one. I would say this is the angle of refraction basis of the way we saw it. It was over 30 degrees, so it had to be 32.5. He must be thinking it's on the other side. Maybe my protractor, but this would be the correct answer. Again, I will make these the correct answer for my classes. I can make an argument for either one. All right, and that's the whole thing. Again, if you have questions, please see me. Otherwise, this is an application grade, so please make sure you take your time with it. For most of my class, I will walk you through that myself. But for others, for first hour, you'll kind of have to rely on the video itself. So hopefully this helps understand refraction a little bit better. I hope you have a wonderful day.